Good morning, everybody. Welcome back after 2 weeks of break, or actually 1 week break, right? I hope everybody had a great time with their loved ones during the Bayram. Now, today we start with Fourier transform. Actually, it's not something really new. You have been, remember, or we've been working on Fourier series representation of periodic signals, right? And the goal is actually to be able to analyze, see, observe, and manipulate frequency content of data, right? Frequency content of signals. And we did that through, remember, finding something called a spectrum representation. Now, Fourier transform does that for actually also for non-periodic signals. Remember, until then, it was more sinusoids, cosines, sines, or periodic signals we could express as sums of harmonically related sinusoids, remember, in Fourier series expansion. Now, actually, it's going to be some of, again, weighted basis functions, Fourier basis functions, but those frequencies have a very wide range of, it could be any frequency, actually. So all kinds of varying frequency oscillations could exist in the signal. That's the thing. With periodic signals, remember, periodic data, if data has some kind of periodicity, near periodicity, even if it's repeating itself somehow, that's a pattern that's repeating itself, we will find, remember, a fundamental frequency, and it's only multiples, integer multiples, harmonics. That's the difference. Now, it doesn't have to be that way. It doesn't have to be a fundamental frequency and it's multiples. That's the difference. So we will study both continuous time Fourier transform and discrete time Fourier transform. For mathematical abstraction completeness, it's easier to start with continuous time. So let's start with continuous time Fourier transform. This will be from chapter 11 of the SP first book, signal processing first. Next time when we go to discrete Fourier transform, that will be from the DSP first book, okay? So this will be continuous time. So Fourier transform. Remember our goal, this is SP first book. Our goal is really to analyze frequency content of non-periodic signals. So, okay, so goal is we want to develop, so maybe let's say, want to develop a general definition, okay? General definition of frequency spectrum. Remember, from actually the first week, since first week, we are looking at spectrum of a signal, right? Frequency spectrum for this time, for any signal. X of t, this would mean both periodic and not non-periodic. Actually, our main goal here will be here, non-periodic, and also periodic. Actually, periodic, we know for periodic signals, we already are experts on Fourier series representation, right? Now, actually, the derivation follows from Fourier series representation. Our textbook has a very nice derivation. Let's quickly do that. Starts with a periodic signal. Recall for a periodic signal. So take any periodic signal. Take x tilde, let's say, of t, any periodic signal. Okay. So I'll just graphically plot it and just assume some graphical form, but it doesn't have to be this guy, okay? So I'll just draw a rectangular pulse like this, but I mean, it can be any waveform, of course, right? So periodic, just to, for us to be able to see, remember, a periodic signal repeats itself, right? This is, let's say, x tilde of t, and it has to have a, here in this case, obviously, this is the fundamental period, right? T0, actually, it's repeating itself every T0 at this point. So this is the fundamental period. So I can find From this T0, remember, I have a fundamental frequency. So here, just for illustration, this square wave is non-zero between minus T/2 to T/2. Okay, and let's say it has amplitude 1. So now what we will do, this is periodic, okay? We'll obtain a non-periodic version of this by taking T0 to the limit, to infinity. So push all these replicas to infinity. So now that's what we do. Non-periodic, obtain a non-periodic signal. So let's do that. It is, I mean, I'll just take the main lobe, of course, in the middle, T. So it's going to be really just this guy, right? T/2 minus T/2. And let's say this guy now, this is x of t, is limit the period goes to infinity of the periodic signal, okay? I think it's obvious, right? We pushed these to infinity. I mean, they are now, as T0 goes to infinity, you see T0 here. I don't have any replica, right? It's not repeating itself. Now x of t is a non-periodic signal. This is a non-periodic signal, okay? So now what we will do is we will start with Fourier series expansion of the periodic x tilde and push T0 to infinity. That's the actually a simple way, an intuitive way to derive Fourier transform. So Fourier series expansion, a simple practical way, okay? What is it? We know x tilde of t. This is tilde signal, okay? Just write the form. You guys know this, so I assume you guys already know Fourier series expansion of a periodic signal ak e to the j k omega 0 t, right? Where omega 0 is, let's write this, 2 pi f0, okay? I mean, fundamental frequency. This is the normalized frequency. Okay, so now I know how to find the Fourier series coefficients. AK is, remember, 1 over T0 in between any period range, right? Any period. So maybe, okay, here minus T0 over 2 to T0 over 2. I can take the signal, dot product it with the conjugate of this basis function, e to the minus jk omega 0 t, and integrate it out, right? That's the Fourier series coefficients. So this is Fourier series coefficients, ak, for x of t, right? For x tilde of t, sorry, because it's for a periodic signal. Now I can do the math just very quickly. Let's do the math. Just in this period, my signal is minus T0 over 2 to T0 over 2 x. Actually, maybe let's write here already T over 2, right? For this example, I'm just doing this now, minus T over 2 to T over 2. X tilde is 1, right? So it's 1 in this interval. Just see, it's 1 here, right? In this range. So 1 e to the minus jk omega 0 t dt. Just let's write the math. It would be actually, I think we've derived this before, sine over sine, let's say omega 0 kt over 2 over t0 k omega 0 over 2. Okay, this is what we have for AK. I'll rewrite this on the next page. You can do this, right? It's simple integration. So you guys can really derive this. Okay, here it was T over 2. So let's rewrite this from here. We'll take that T0 next to AK. Okay, here this T0 comes next to AK, multiplies AK, sine K omega 0 T over 2. What I'm trying to do is I'm going to show you now. We will look at this coefficient, Fourier series coefficient, and we will see what happens to it as t0 goes to infinity. So now this is a discrete spectrum, remember. So this is omega, this is AK times T0 I'm plotting, okay, this guy. And it's gonna have an envelope like this. Probably you guys can check the book for a better envelope, but anyways. Maybe let's do it a little bit. It's dying, right? Remember, these are. Now, this is actually when I'm plotting this guy, okay? So it's gonna have its maxima at 0. This is A0, T0. So that's 0, let's say omega 0, 2 omega 0. Let's say, I'm just making this up to omega 0, 4 omega 0. I mean, of course, depending on omega 0, it's gonna have different frequency positions here. Here also it should be just symmetric. Just okay. So this would be this sign, like sine omega over omega type function, right? Yeah, it's a sinc-like function. So this is the envelope. The envelope is this guy, of course. But it's discrete itself. Remember, for a periodic signal, this is for periodic x tilde of t. So now what I want to try to see is, now as t0 goes up, remember we said let's make the period of the signal very large. What happens to omega 0? Omega 0 goes down, right? So I will be sampling this thing much actually frequently. So it's gonna be actually just let's show this envelope again. I mean, it's really, the goal is to show this. Now it will be, you see, the goal is try to see for what is happening for a non-periodic signal. I'm trying to push this spectrum towards pushing the period to infinity. So it's becoming a non-periodic signal, right? So as t0 goes to infinity, omega 0 actually, this guy will be like my differential, this delta omega, you can maybe say, I mean, so this is really becoming my continuous variable. That's the idea. So my spectrum becomes denser, and hopefully in the end the goal will be that it's gonna be approaching the envelope, right? Envelope of this AK. That will be the goal, denser and towards the envelope of the AKT0. Okay, that's the goal. So this is what we will be doing exactly. As T0 goes to infinity, AKT0 goes to envelope. In this case, e.g. for this one, it's sine omega t over 2 over omega over 2. And this is equivalent to the continuous time Fourier transform of x of t, of course, not non-periodic signal. So this is it, guys. We will say, hey, as t0 goes to infinity, omega 0 goes to d omega, and k times omega 0 becomes my frequency, continuous frequency variable. So these are k times omega 0, right? They will go to my omega. This is continuous frequency variable. Remember, for a periodic signal, we have only spectrum non-zero at discrete frequency positions, right? K times omega 0. But now I will have a continuous frequency variable omega, And R, remember, we had this guy, AK times T0. So this guy was minus T0 over 2 to T0 over 2, right? X tilde of T, this was the Fourier series coefficient formula. Now, this guy, we said its envelope, we already called it continuous time Fourier transform. We will name it x of j omega. This is continuous time Fourier transform of the non-periodic signal x of t. This is non-periodic, but I can calculate a Fourier transform of both periodic or non-periodic signals. Now t0 goes to infinity, right? That is what we did while going from here to here. Now, minus infinity to infinity, this guy becomes x of t, right? Because limit t0 goes to infinity, x tilde of t was really x of t, the non-periodic signal. Okay, this was the idea. So now e to the minus j omega t dt. So this is really the definition of, I mean, this is really not the most rigorous mathematical derivation, but this was what our textbook actually showed as an intuitive derivation going from a periodic discrete frequency spectrum, right? For a periodic signal, push to period to infinity, you see we are approaching the envelope of that. You see a continuous approximation of that frequency spectrum. This is the idea. Actually, I really like this derivation. That's why, I mean, it's an intuitive derivation. We could have just defined it actually. We could have said it's really the definition of Fourier transform, continuous time Fourier transform of x of t. I mean, we could really just say x of j omega is defined to be, take the actually inner product, right, of your signal with the, in this case, the basis is e to the minus j omega t, and integrate out. Actually, inner product for function spaces is involves an integral, right? So that is the continuous time Fourier transform. So maybe let's try this. Continuous time Fourier transform. So this is called, this is the acronym. So here important thing is note x of t is not periodic. Is not a periodic signal. So you see continuous time Fourier transform, I can really calculate it for any signal. That's it. That's nice. It is a Fourier transform, so not a Fourier series. The periodic signal. So let's write it has a Fourier transform, not a Fourier series. Okay, let's write this. And still also xj omega shows us the frequency content, shows the frequency content. Okay, so this is really what we've been doing from the first week, since the first week. Now our Fourier transform shows the frequency content, and this is, remember, what we've been calling really spectrum representation of a signal. So Fourier transform, maybe actually just say Fourier transform is gives us a tool to create a spectrum representation of the signal, right? Again, that's something we know. Now we know how to go from x of t to Fourier domain, right? Time domain. Now we learned actually time to frequency domain. Time to frequency, but it should be something, such a tool to be useful, we should be able to go back. So forward was Fourier transform. This was time domain, frequency domain. Okay, this is Fourier transform. Now I want inverse Fourier transform. Let's derive this very quickly too, okay? So inverse Fourier transform. How to find that? So let's derive that now, if there are no questions at this point. Any questions? I mean, we defined it already. So, and you see, we've come through a derivation of coming from a periodic signal spectrum to a non-periodic signal spectrum. Now, how to go back from, this is what we want, xjw to x of t, okay? So inverse Fourier transform. So that's what we want. Because we should be really able to do this, go back and forth. This time, guys, we will say, let's start with, okay. So let's say xj omega is the Fourier transform, okay, of a non-periodic signal x of t. Just for illustration, let x of t between, okay, just say, you see, I mean, its form is not important. I'm drawing a triangular waveform, but let's say I have this signal. Just say, okay, an example. Now, we will create this time a periodic extension of this guy. Remember, in the first derivation, we started with a periodic signal. From there, we went to a non-periodic. Now, construct, let's say, periodic extension. A periodic extension of x of t, that would be really this guy, right? So let's maybe plot it here. So I would have this, and it would be really repeating itself again in time. So let's call this again x tilde of t, right? And it's really repeating itself. It was a t0 period, and it should probably it's here touching. I already, anyways, I mean, it's not really up to scale. So our periodic expansion, actually, we can write it as, for in terms of x of t, sums of shifted x of t's, right? So it's gonna be really xt minus k times t0. So this is at 0. Let's say this is at t0 minus t0. There will be a version at minus t0, etc., right? And here 2t0. Anyways, so this is, remember, for a periodic signal, it repeats itself infinitely. Now, Fourier series, I can find its Fourier series coefficients. Find Fourier series coefficients of this guy. I know it is ak 1 over t0 minus t0 over 2 to t0 over 2, x tilde of t, right? E to the j minus j k omega 0 t dt. This is my Fourier series coefficients, right? Equation. Now I want to rewrite this because it's in one interval. It's really x of t, right? 1 over t0. I can really say minus t0 over 2 to t0 over 2. It's x of t now. You see, I replaced it by x of t. Guys, please check. You see, now it's here. Now I can also make this minus infinity to infinity because I know x of t is 0 outside, so it doesn't really matter. Now I have, from here, guys, I have, this is really, I know, Fourier transform, but with, okay, this is 1 over t0. This guy is really Fourier transform at multiples of the fundamental frequency. Do you see? I just applied the definition. Okay? So from here, we found the relation between Fourier series coefficients and the Fourier transform of a periodic signal, actually. You see, take the Fourier series coefficients, multiply them by t0, you get the Fourier transform at these multiples of the fundamental frequency. So this is really, let's say, relation between Fourier series coefficients of a periodic signal, okay, coefficients of a periodic signal and Fourier transform, and the Fourier transform of a non-periodic, or let's say corresponding signal of the corresponding signal in one period and zero everywhere else. This is important. Zero everywhere else. Okay? So you see, I just did that here. We took this, right? We took this and we just said, I'm taking one period of this signal and creating a non-periodic signal like this. Or we started with the non-periodic signal or replicated it. It's the same idea. Now, how to obtain x of t from x of j omega? Let's go back to that question. We will use this. Okay. So if you are fine. So now question again, can we obtain x of t? I mean, we are continuing to answer this question. How to find, this is called inverse Fourier transform, by the way. Inverse Fourier transform also, that means, or let's say IE. Now let's again start with this x tilde, the Fourier series expansion, ak e to the, I mean, x tilde is periodic, so I can always write its Fourier series expansion. Now I'm gonna insert the Fourier transform here, okay, which is this xjk omega 0 over t0. So insert this xjk omega 0 over t0. So this is, let's say, insert what we've just found. Insert here what we've just calculated on the previous page, okay? So now, guys, this was k minus infinity to infinity e to the j k omega 0 t, okay? Now, what is t0? T0 is 2 pi over omega 0, right? Insert it here. This was k. So I will have 1 over 2 pi, because t0 is in the denominator, right? X, j, k omega 0, the spectrum at multiples, or the discrete spectrum, because it's for the periodic signal. Now, e to the jk, we will take limit as in the previous one, times omega 0. Remember, we had said, I mean, this is not exactly very rigorous mathematical proof, but it's nice, still intuitively fine. We said, remember, as t0 goes to infinity, look at our, okay, maybe spectrum. Remember, let's say, I mean, I'm just making up a spectrum here, okay? I will look at this discrete spectrum, actually, meaning this is xj k omega 0. Let's say if here this is xj k plus 1, let's say. Right? So this is really k omega 0, k plus 1, omega 0. And as t0 goes to infinity, we remember we said I can treat this differential or delta omega 0, right? As omega 0 goes to, as t0 goes to infinity, my omega 0, I can treat it at like, as a, maybe let's say just delta omega or d omega. And that will go towards 0, right? It's going to be a differential frequency element. So this is a little bit calculus, but also not very rigorous, but still makes a lot of sense. K omega 0, I can treat it as my continuous omega variable. Now do the math, because this is, remember, what helps me go from x tilde periodic signal to the non-periodic signal, right? This is how we went there. And if you do this limit, take the limit, taking the limit here, I would just say, actually, now move from sums of these spectrum, right, at K spectrum points. So I was actually showing this guy here, right? For different K, you have these guys. Now we go to an integral minus infinity to infinity. This was K from minus infinity to infinity. So now I have x of j omega e to the j omega t d omega. So this is the definition of the inverse Fourier transform. It's something we expect. This is like a normalization constant, guys. That's something that turns out to be there, 1 over 2 pi. But other than that, it's something I think you could expect when you remember how to calculate the Fourier series coefficients, right? They were, or the, no, the extension, sorry, when you look at this guy. We went to a, from the sum, we went to a integral, right? This was Fourier series expansion, right? So these are like my Fourier series coefficients, but now for a non-periodic signal, of course. For a non-periodic signal. And these are the basis functions you see, and similarly here they were. This is called inverse continuous time. This continuous time Fourier transform. So this is, you see, helping me go from xj omega back to x of t. Okay? Again, so these are like my Fourier coefficients. These are like my spectrum coefficients. Okay, spectrum coefficients. These are my basis functions. So you see, I'm doing again a signal decomposition. X of t is decomposed into spectrum coefficients times, right? Or projected onto these basis functions. Spectrum coefficients times basis functions, weighted addition, or in this case, it's integration, because it's the continuous time Fourier transform. So now at this point, are we fine? We have defined both ways of this Fourier transform, going from both time domain to frequency domain and also frequency domain, okay, time domain to frequency domain. We can go both ways. This is nice. And there is a one-to-one relationship, okay? The importance is, guys, now I can work either in time or frequency domain, whichever is useful. For instance, remember, for frequency domain or frequency selective filtering, I would want to work in frequency domain, right? For signal manipulation, maybe, for instance, compression. Remember, for signal compression, if you want to compress things, you would work in frequency domain, for instance, one idea, and you would suppress all those components, coefficients that have small magnitude, right? Small Fourier transform, for instance, coefficients. Then you would go back to reconstruct the signal. Okay? So this is forward Fourier transform, and this is inverse Fourier transform coming back. This is important to have this actually one-to-one relationship. Also, existence of Fourier transform. We have a sufficient condition from the sufficient condition exists. That is, from the definition, Fourier transform exists. Maybe let's say start it here. Fourier transform exists when the signal is absolutely integrable. dt is finite. Okay, so that is this sum or integral is finite. Okay, when this integral is finite, we know its Fourier transform exists, but this is a sufficient condition. There are signals like, for instance, cosine or like step function, which are not absolutely integrable, but whose Fourier transforms are exist. So this is a sufficient condition, not a necessary condition. Okay, not a necessary condition, because, so what this says is, when if the signal is absolutely integrable, I'm trying to say absolutely integrable, I know definitely that its Fourier transform exists, but not a necessary means, but there are signals, guys, where we have the Fourier transform and which are not absolutely integrable. That are not absolutely integrable. For instance, we will find the Fourier transform of cosine omega t, let's say. I mean, it's the sinusoidal, good old sinusoidal signal. We know it's periodic, it has infinite extent, right? It's not absolutely integrable, but its Fourier transform exists. Or forms of, I mean, it could be forms of cosine, but it's, or actually this one, this is maybe a better example, step function, but its Fourier transform exists, okay? So guys, now we learned the definition of Fourier transform. Actually, it was, let's rewrite it here, minus infinity to infinity x of t e to the minus j omega t dt. You see, I'm getting rid of integrating everything about time. And the inverse one is actually, remember, x of t is 1 over 2 pi, again, minus infinity to infinity, x of j omega e to the j omega t d omega. This time, I'm getting rid of everything about frequency to get time into time domain. Here, I'm integrating everything that is related to the time to get the Fourier or frequency domain representation, okay? So once we start continuous time Fourier transform, what we do is, guys, we start to build now. Now we start to develop typically how people work in signal processing is we start to develop a library of Fourier transform pairs for an efficient processing actually. So for instance, now if I give you this signal, a little bit math, calculus math, but it's really fun math, I mean, not difficult at all. I'm asking you, find its Fourier transform. What is its Fourier transform? Now you know the definition. You can say, hey, I know I can really calculate this guy, u of t e to the minus j omega t dt. So you guys will just write this is 0 to infinity e to the minus 5 plus j omega t, right, dt. And then do the math here. I'll just write the result. It's going to be 1 over 5 plus j omega. Okay? So you see e to the minus 5t u of t, you will say, has a Fourier transform, or maybe let's say it here. So you see e to the minus 5t u of t, this was x of t, its Fourier transform. This is its Fourier transform, right? And it's going to be one-to-one relation. Okay, maybe let's write it here, the integral result, so you guys can do the math if you want, okay? And this is generalizable. This is called Fourier transform of a right-sided exponential because of the u of t, e to the minus at u of t, its Fourier transform is 1 over a plus j omega, but for a positive. Why? Because, guys, this is let's say, the exponential, right? Right-sided exponential. E to the minus at u of t, right? It's all zeros here. It starts at actually for t equals 0 at 1, right? And it goes, I mean, it just decays. Here, we can look at the h of j omega. Let me plot the magnitude response. Okay, so let's put a positive here, okay? A positive, so I'm gonna, this is h of j omega. From here, let's look at the magnitude response. Okay, 1 over, this is it, right? Guys, this will have something like this. I'm just making this up, but please, again, these are all in the book. This is the magnitude response. So I'm looking at this signal both in time domain and in the frequency domain. Okay, so time domain and frequency domain. Representation of this signal. What is a good observation here is, let's try to increase A. This exponential signal will have a faster decay, right? So it's going to be more localized in time. I mean, as I increase A, it's going to decay very fast. So it's going to be non-zero only for small parts of the time range, time domain. But it will have a vice versa effect. Guys, it will start to have a wider spectrum as we increase A. Okay? So this was increasing A effect. As A increases, we see this effect here. But as A increases, we have a wider frequency coverage. So this is called actually time, let's say, narrow. If I have a narrow in time, a signal narrow in time, make it narrower in time, I will have a wider spectrum. Sometimes we call this bandwidth. Bandwidth will be higher. Bandwidth is larger. Guys, bandwidth is typically that something that where we have, for instance, if I had some A here, the amplitude, the maximum amplitude, when it falls to something like, for instance, 1 over square root 2, this range is approximately my bandwidth. I mean, after that, what I'm trying to say is the spectrum gets closer to 0. So wider spectrum, and it's vice versa. Narrower spectrum is wider in time. This is due to Heisenberg uncertainty principle, guys. Narrower in frequency, then that signal we know is wider in time. This is the duality between time and frequency domain. The domain, this is due to Heisenberg. You see, we tied to a famous physician, Heisenberg uncertainty principle. Remember, he was saying, his postulate was, you can't really simultaneously improve your resolution both in frequency and time domain. You have to compromise. You either resolve the signal very well in frequency domain, then you are not really resolving it well in time domain, and it's vice versa. Okay? This is something that is known. Due to this, I can repeat, signal, if signal is wide in time domain, we will see this again and again, don't worry. And it's gonna be narrow in frequency domain. is narrow in frequency domain. And now narrow wide. And if it's wide in frequency domain, it's going to be narrow in time domain. Okay? So this is something we will be seeing a lot. So narrow in frequency domain, we can say its bandwidth gets smaller, and here its bandwidth gets larger. It's equivalent to say that. Okay? Signal bandwidth. So maybe let's write it for your notes. Bandwidth, signal bandwidth, okay? Gets large. Then signal gets narrow. So I think we can maybe give a short break, or at least still 10-minute break to get coffee or something. Any questions until here? Guys, let's see. Let's pause the let's get started. We have material to cover, so we can chat later. Okay, so I think, let me see. I thought I shared, but no. Let's share it. So let's continue now by building our library. This was actually first example we did, a right-sided exponential. Remember, if it's a left-sided exponential, then I need actually B, let's say A would be less than, or let me see. Let me note this, guys, for you. Just note, yeah, for a left-sided exponential exercise, or let's see, this is an exercise for you guys. Now, show for a left-sided exponential signal. So that will be x of t, little x of t, e to the bt u of minus t, right? It's left-sided, so it's going to be really this guy. It's 0 in this side, on the right-hand side of the positive time axis, right? And in this case, again, b is positive here. In this case, please show its Fourier transform. Its Fourier transform is given by, this time, 1 over b minus j omega. Okay, you guys can, but the same things hold here, the same relations hold. You see, its magnitude response will be same, right? It's gonna be really 1 over b squared plus omega squared. So I mean a squared plus omega squared. So it's really gonna be a similar Fourier transform. This would be the x. Okay. So you can exercise show this. Okay. Now the second signal we want to do or derive. This is, you see, really nice mathematical exercises. I hope you're also enjoying it. It's really not difficult for you at all. I mean, as the computer engineering, computer science students whose math is probably at the highest level among all IT faculties. So I would assume these are really not difficult math for you at all. Okay, but guys, I'm saying this, don't get me wrong, you have to study on it, of course, right? I mean, it's not like nothing is like coming naturally. It's really some things that you should sit down with pen and paper and derive. So what is the Fourier transform of this square or rectangular pulse signal, for instance? Okay, because this is like a windowing signal, ideal window-like signal, right? This rectangular pulse, to extract a certain range of a signal. We want to find, for instance, I mean, it's a classical standard signal that's used, so we want to find its Fourier transform. just apply the formula. I mean the definition, right? Minus infinity to infinity x of t e to the minus j omega t dt. Just insert it here. So it's really non-zero in some range, and it's really 1 in that range. dt. Now do the math. Should we do the math? Okay, why not? E to the minus j omega t over minus j omega. Bring my integral limits here. You can here manipulate to find sine. It's a sinc function. Omega t over 2 over omega 2 over 2. So I want to plot this now. This is my, okay, this is dot, dot, dot. So this is the Fourier transform of the this rectangular pulse, okay? This guy. So let's plot this, guys. Omega. At omega equals 0, there is a 0 in the denominator. We use L'Hopital rule, remember? Right? For omega 0 value, I can take derivative of both numerator and denominator. So use L'Hopital and then find t over 2 cosine omega t over 2 1 over 2 in the denominator. I have t, for instance, so it's gonna be t here. I mean, again, there are nice plots in the book, so I'm gonna really be, these are fading away, but it's still an infinite extent. I mean, they are fading, but still, these are the main lobes. So this is t, this is x of j omega. And where is it 0? You can just find it from the sign, guys. It's multiples of 2 pi over t. Okay? So the zeros can be found from wherever this guy is 0, right? So you should just from here check that this is multiples of pi k, and when omega is 2 pi k over t, zeros of this Fourier transform. Okay? This is then 4 pi over t, 6 pi over t, minus 4 pi over t, minus 6 pi over t. Okay? So typically for this sinc signal, sinc function, the bandwidth is like between these two, or the main, what we call the main lobe. This is like the bandwidth, main lobe. I mean length or width of the main lobe. So it's really almost like 4 pi over t here. So what I want to show here is also again this inverse relation. Note. So x of t was this guy minus t over 2 to t over 2. So again, note this bandwidth was here 4 pi over t, right? Sorry. Guys, check this out. Now I'm saying in time domain, if I increase t, the width of the signal, right? This is the width, which is t. What happens to the bandwidth in frequency domain? So increase the extent of this signal in time domain, its bandwidth will get smaller, right? That's what I'm trying to say. So again, here, let's note this. As t increases, so it gets wider in time, you see narrower in frequency. Narrower in frequency. Why? Because bandwidth gets smaller. And vice versa, t, the time extent gets reduced, bandwidth of the signal in frequency increases, right? The same relation we can note here. So let's do a little bit more math. This Fourier transform at first is a lot of math, but you guys are, of course, using this numerically, right, in your data analysis. So currently we're just looking at the mathematics behind it. Even now we started from the continuous mathematics, more like a mathematician. Mathematicians start from this continuous, but engineers sometimes skip this continuous part, go directly to discrete version, but I believe it's very educational for you to know the continuous math too. Okay, that's why we are studying this now. I keep repeating this, but guys, as computer engineering graduates, I expect you to be really very proficient, very good in math. You should really shine among others. When you graduate, you should have a distinction among other people around you, other engineers, other scientists, by your hopefully good math. Okay? It will always take you a few steps ahead of other people. That's why. You should be confident in math. So let's say this is x of j omega. This time I'm giving you the Fourier representation of the signal. You see, this time it's actually a pulse or rectangular pulse in the Fourier domain. Actually, remember, this is really a low-pass filter, right? Ideal low-pass filter. So remember, recall, this is a ideal low-pass filter. Pass filter. Okay? So I'm asking you, or we're trying to do this exercise of what is the low-pass filter in time domain actually. We should try to understand, you know, what kind of a signal is that. Okay, so we just this time apply inverse Fourier transform formula. It's really simple actually. We're doing straightforward mathematics here. X of j omega e to the j omega t d omega, right? I'm trying to integrate out the frequency variable. Now it's easy integral because it's band limited. It's minus omega b to omega b in a certain range. It's non-zero only. It's 1 there, e to the j omega t d omega. Let's just complete the math here. E to the j omega t, the denominator will be jt, right? Integrating it out from minus omega b to omega b. I think this is something you guys already relate to. This is 1 over pi t. Okay, there was a 2 pi here. J will go on this side. There will be 2j because we'll get a sign. E to the j omega bt minus e to the minus j omega bt. And this is, what is this in parentheses? It's a sign, right? From Euler's formula. I think everybody can see or recognize this. So my x of t is 1 over pi t sine omega bt. Okay? So again, a sine t over t type. So this is a sinc note. This sinc function, remember, sinc x is sine pi x over, this is the definition, over pi x. So again, this is a sinc-like function. Maybe let's write this on top of the numerator, sine omega bt over pi t. Okay? So let's plot this. Again, I'm expecting a sinc form here. Now I think you guys know a sinc, but this is x of t. This time it's in time domain. Okay? Again, I mean, it's not easy to draw this beautifully, but just doing my best, etc. So this is 0. You can find what this value is. It's omega b over pi here at this point. So let's maybe, that value is that. Here it is. These are important. You can find it's 0 crossings. You see, inversely proportional to the bandwidth length omega b. 2 pi over omega b as we expected. You see again the inverse relation, okay? Etc. Minus pi over omega b, pi over omega b minus 3 pi over omega b, and then it continues in this way. What do you observe, guys? For the ideal low pass filter, the time domain signal is infinite length. For this is, and the name implies this is ideal low pass filter. The filter in time domain is infinite length, guys. I mean, you can think of this as the frequency response, right? I mean, this is like h of j omega, right? Frequency response. E.g., I'm saying, I mean, it's Fourier transform of the impulse response, right? So this is filter in time domain. Equivalently, this is my impulse response. You see, it is infinite length. Infinite length. This guy, I mean, look at this signal, right? It continues plus minus infinity. Therefore, you see, ideal filter is not realizable actually. Is not. Typically, we could truncate such signals, or we don't aim for such infinite discontinuities in this filter. Okay, these are just some idealization, abstraction of what we would want. Also, let's note, again, time frequency duality. The original frequency response or Fourier transform, this was the Fourier transform given. Right, it was, for instance, let's say this guy, minus omega b. Now let's again do it was 1, right? 1. This was the bandwidth. So if bandwidth, for instance, increased, so that's omega b increased, what happens to the main lobe here? It's gonna again shrink, right? So bandwidth increased. This is wide in frequency domain, wider in frequency domain. Again, narrower in time domain. And again, vice versa. Wide in time would be narrow in frequency. I think you guys can see this. Bandwidth increase, this guy would be decreasing. Okay. By the way, this ideal filter is not realizable, so these frequency selective filters recall practical filters were. That's why they don't have these excellent jumps, discontinuities. They have these ripples, you know, some transition band, some maybe ripples here too, right? I mean, this would be something in practice, what we see. We don't see this beautiful infinite jump at the actually cutoff frequency, right? Remember, this was cutoff frequency. So typically this is a practical filter. Okay? Practical low pass filter, of course. Okay. So now let's do, I think we did both ways, right? Pulse in square or rectangle, pulse in time or frequency domain. And now let's look at Fourier transform of the impulse function. I think we've done this a little bit, but in frequency response, maybe. Oh no, maybe not. So what is Fourier transform of delta of t? We've studied delta of t at that topic in that part. So what is this guy? So let's see. I mean, let's just apply the Fourier transform definition. dt, of course, come on. Yes. Now, minus infinity to infinity, delta of t. remember, impulse samples, right? It has a sampling property. It will sample the signal. It is multiplying at t equals 0. Samples at t equals 0. And it's integrated. It's 1, right? So it will be actually 1. Maybe I could say this. It's actually this guy. Delta of t times 1 dt, and we know from sampling property this is equal to 1. That's from the definition of the delta, remember. Area underneath is 1, right? This is it. So actually, we've just got this well-known relation. This is the two ends of the spectrum, the narrowest possible signal in time, guys. This is really, remember, we showed this delta as delta function in time. This is the narrowest possible signal in time, right? This was a perturbation. Remember, this is a signal that is on and off. It has an infinite amplitude actually, but its area underneath is 1. This is an abstraction actually. Now in frequency domain, it is the widest possible. This is x of t, and it is all frequencies. It's a constant, right? All frequencies. It's equal to 1. This is widest possible waveform. This is the widest possible waveform in frequency or signal in frequency domain. Okay. Now you can ask the dual relation. Now what is then Fourier transform inverse of delta omega? What if now I have the narrowest possible signal in frequency domain? Right? I can ask that question. I'm asking you now, vice versa. Start with delta of omega, okay? I'm asking what is the signal, what is x of t here? You can guess from the duality. You see, this is a signal with only, in the frequency domain, the frequency spectrum has only 0 frequency, right? So what kind of a signal in time domain has 0 frequency? Constant signal, right? No oscillation, constant. So that will be actually a constant. Exactly. Let's do the math. Let's leave a place here for plotting that thing. Okay, t, it's gonna be t. Sorry, t. Now let's do the math here. 1 over 2 pi. Let's apply Fourier transform inverse. It's really x of t. Sorry, x of j omega, of course. I'm starting from the Fourier transform. Right, this is what I need. I have 1 over 2 pi delta omega. It's doing the same thing as we did in the time domain, right? It's going to sample from this guy, which will be 1 over 2 pi minus infinity to infinity delta omega d omega, which is this time 1 over 2 pi. Okay? That's it. So this will be here 1 over 2 pi, and it's all constant actually. This is x of t. Okay? And this is the corresponding Fourier transform. Okay? So, so forward is Fourier or backward is inverse Fourier transform. Again, you can see that here it was widest in frequency. Now here it's narrowest in frequency. So let's don't confuse these two examples. Now narrowest in frequency. This is widest in time. Okay? So now the relations were, this is one relation, Fourier transform relation. Now another one is 1 in time domain goes to 2 pi times delta omega in frequency domain. Okay? This is time. This is frequency. Okay. I mean, signal has 0 frequency, right? I mean, this signal has 0. I mean, its frequency is equal to, has frequency equal to 0. I mean, that's what I'm trying to say, right? Frequency is 0. So now, any questions until here? We're calculating Fourier transform pairs, right? I mean, nothing really magical. It's this was 5, now 6. I can look at the shifted impulse. Actually, guys, now you can drive this. Okay. What it's Fourier transform e to the minus j omega t0. Now you guys can do this, or let's do one of these. We'll do vice versa. I'll start with 1 over 2 pi e to the j omega t0, and its Fourier transform pair will be a shifted impulse. So shifted impulse in time domain went to a complex exponential in frequency domain. Now a shifted impulse in frequency domain goes to, again, a complex exponential. Okay, so maybe we can do this. Okay, let's maybe just show one of them. Let's start with the second one, Fourier transform inverse. So this will be really 1 over 2 pi minus infinity to infinity delta omega minus omega 0 e to the j omega t d omega. Remember, again, this guy multiplies and samples from this, right? So this will be e to the j omega 0 t, right? D omega. So I would have delta also there, of course. Sorry, delta should be staying here. It's a sampling, first sampling property. E to the j omega 0 t. Now this guy I know is just sampling the signal at that value. I mean, there is 1 over 2 pi, of course. Over 2 pi. That's good. I mean, from here, you guys can recall then a complex exponential in time will be 2 pi times a delta in frequency. Maybe you can remember it in this way. You won't have to memorize these, by the way. Always we open up and look at a table. These tables are in your textbook. But knowing how these things are derived is a good mathematical practice, okay? So now once we know this, I'm going to ask you the Fourier transform of the cosine. Guys, can you please answer? X of t is cosine omega 0 t. Okay, by the way, this was, sorry, omega 0, right? Please correct me. The omega 0 t, right? Because you see, t0 was in the first one, guys. Here it was t0 shift. It went to the frequency domain. Now it's frequency shift by omega 0. You see, it translates to the complex exponential's frequency, please. Yeah, this is important. Now, what is then the Fourier transform? I'm asking you of this guy, of the cosine. I think it's obvious, right? You can use property 7 or this pair, Fourier transform pair 7. Fourier transform, inverse Fourier transform. How can I expand this x of t by Euler formula, right? I can expand it by, so x of t is really 1 over 2 e to the j omega 0 t plus 1 over 2 e to the minus j omega 0 t, right? Now, it's easy, right? It's pi. You guys should just directly see it. This plus pi delta omega plus omega 0. It's two shifted impulses, right? Cosine Fourier transform. This is what we expected from before, but now we wrote it in terms of the Fourier transform. Let's plot this guy. The frequency spectrum or Fourier transform of the cosine omega 0 t. I will have two impulses at omega 0, and it has an area pi, and okay, it should be symmetric, of course. Minus omega 0, and again pi, right? These are delta. This time you see it just becomes a delta. It becomes a delta function. I have to note this. Note or recall, I should say recall here. Recall again from the first few weeks of this course. Frequency spectrum of the cosine. We've calculated this, right? The spectrum. The good old frequency spectrum of the cosine omega 0 t. It was actually the same thing, but notation was different. We were saying, actually exactly as in here, we were saying, hey, I have at omega 0 and minus omega 0. We were saying this is 1 over 2 and 1 over 2. Remember, because we were really picking these coefficients and plotting everything, right? Remember, at those frequencies, it's, I mean, just the scalar difference here doesn't matter, really. Fourier transform or frequency spectrum. I mean, it's really important thing is I have these, I mean, this is like also Fourier series, right? Because we will have that relation between that. Fourier series is also the same because cosine is a periodic function, by the way. We don't have Fourier series for the others until now. They were not periodic functions. But because cosine is periodic, it also has a Fourier series and it amounts to the same thing with a different scalar, right? Weight. There is a pi multiplying. Okay. For instance, now I can ask you as exercise, guys, exercise, find the Fourier transform of, I'm giving you x of t is sine omega 0 t. What is the Fourier transform of this signal? You would just go and say 1 over 2j e to the j omega 0 t minus e to the minus j omega 0 t, and from here map it, right, to the corresponding delta functions. So actually, guys, maybe I can remember, you should just remember this relation. Recall, just use this. Sorry, guys. You should just recall this. Okay. So recall this guy. It was 2 pi delta. 2 pi times a shifted impulse to that frequency, right? Shift the impulse to that frequency. So now do the same with these two guys. It's going to be 1 over or pi over 2, right? Pi over 2. I need e to the minus j pi over 2, right? With that guy. Okay. 2's cancel actually. There is a 2 here. It's going to be just pi. Okay. Pi to the minus j pi over 2 delta omega minus omega 0. Now I have a minus, but I can put that to, yeah, maybe let's make it plus pi e to the j pi e to the minus j pi over 2 delta omega plus omega 0, right? For instance, I mean, exercise, please do this on your own. Okay. So now let's do I had a note here. Okay, maybe let's plot it also. So, because it's gonna be at fundamental frequency multiples. Here it's just the first fundamental frequency, but x of j omega you see here is pi e to the minus j pi over 2 at omega 0. It's another impulse at this time pi e to the plus j pi over 2, right? It's a complex conjugate of each other. Remember these coefficients. Minus omega 0. Actually, the spectrum, so for periodic signals, let's note this. For periodic signals, the Fourier transform, guys, the Fourier transform consists of weighted impulses at harmonic frequencies. Here it was just one harmonic frequency, but harmonic frequencies, I mean, that is multiples of omega 0, right? I mean, that is k omega 0, of course, however many k, where the weights are, where their weights will be 2 pi ak. You see, it's really, the relation is Fourier series. Remember, we said for the cosine, Fourier series coefficients were 1 over 2, 1 over 2. Now multiply it by 2 pi, right? We had the Fourier transform. For periodic signals, we have this simple relation between the two. So, for instance, we can do actually two examples. Let's look at an example where we have a periodic signal, square wave, periodic. Let's plot this guy. T, I think we've started with today with this signal, remember? Minus t over 2, t over 2. Yeah, it was repeating itself at every t0, minus t0, minus or plus 2 t0. This is periodic, right? So let's say t0 is given by 2t. It's, I mean, this is just a parameter given. Then omega 0 is 2 pi over t0, which is 2 pi over 2t, which is pi over t, the fundamental frequency of this square wave x of t. Now the question is, what is the Fourier transform? So calculate Fourier transform of x of t. We know actually, if I know AK, Fourier transform will be, you see, AK times 2 pi. So AK, this is, recall, we derived this already. We did this before. It's Fourier series because it's periodic before. Fourier series coefficients AK are given by, you can do this, I mean, even if we did not do the exactly same signal, but I believe we did this, pi k, okay? K not 0 and k odd here. Then we have for k equals 0, it's equal to 1 over 2, and it's 0 for k even. This was the Fourier series coefficients for periodic signal x of t. So now from here, we know the Fourier transform. Now the Fourier transform of x of t is related to this guy by weighted and shifted impulse functions. It is really 2 pi ak. You see, I need delta omega minus k omega 0. Okay? This is what we have. So for this specific case, let's calculate this guy. So maybe I should, for your notes, put this in. Of Fourier transform of periodic x of t, you see, you can show this is the case. I think at the beginning we did this. So now that would mean find Fourier series coefficients and then take weighted impulses, right? Shifted to those corresponding harmonics, multiples of that. This is fundamental frequency. Because it's a periodic signal, it has a fundamental frequency and it's harmonics, right? So now for this specific case, our Fourier transform, okay, let's add some pages here. So we will have x of j omega, our Fourier transform will be pi delta omega plus, I'm just inserting the form of the Fourier series coefficients into here. K, you see at k0, it was 1/2, so it's going to be pi delta omega. K from minus infinity to infinity, K not 0 and K odd. Okay, 2 pi's or 2, this was 2 pi. I'm inserting the AK. Okay, pi K, pi is cancelled here, times delta omega minus omega, K omega 0. Guys, it's not really difficult. This is AK. I'm inserting AK, okay? That's it. AK we are already given. So that would be, again, as I think we would expect, the square wave to sink relation, right? And it's a dual relation. I can put its, again, envelope, but it's going to be a discrete spectrum. For periodic signals, guys, because it's something that replicates itself, there is a compact frequency domain representation. It's not a continuous one. It's really just non-zero only at multiples of the fundamental frequency. You see, even if xj omega, it's a continuous time Fourier transform, I will have these shifted impulses, right? Pi of delta omega, this one. So I can say, hey, this is 0, this is omega 0. I think this was 2 omega 0, 3 omega 0. This omega 0 was pi over t. You can see these are the zeros of this envelope. Pi over t for pi over t, or yeah, 4 pi over t, or which is equal to 4 omega 0. Okay, so there is 1 here, 5, this is 6 omega 0, etc. And we have the same thing here. The 0, this was 2, I think, here at this point, 2. Etc. I mean, you guys get the point. Okay, so you see I have discrete spectrum, although this is a continuous time Fourier transform. Although this is continuous time Fourier transform, for periodic signals, we end up with a discrete spectrum still. Okay, that's what I'm trying to say. I mean, it's a compact spectrum because of the fact that this thing is really related by harmonically related, right? Multiples of the harmonics of the fundamental frequency. So now let's do a final example where we want to look at find what is the Fourier transform of periodic impulse train. It's already periodic. When I say impulse train, it's a impulse function separated by some given period. Impulse train signal. Okay. So this guy is given by this guy. One, let's say, it's repeating itself by, for instance, every TS seconds, okay? And it's an infinite extent. When you see these TS seconds, what do you remember? Why am I, or why would I, you think, need such a signal? What could be the purpose of such a signal? Give you a hint, you will multiply this by another continuous time signal. What could be its purpose? These are all ones. Can you just imagine what its purpose would be? You see, this is important. This is TS. Every TS seconds. Delta, when multiplied by a signal, samples from the signal, right? This is used for sampling. Ideally, we will talk about sampling problem soon in Fourier domain. We will take any continuous time signal. You know, I always say like a music signal, you have a microphone, your voice, all these physical signals. In mathematical representation, abstraction, we are multiplying it by an impulse train, infinite impulse train. It will sample every TS seconds, right? That really helps us actually in our mathematical modeling. Used for sampling. We will see sampling signals, continuous time signals, okay? We will do this later in the coming weeks. I can write this mathematically as this x of t as shifted delta shifted to every TS seconds, right? Shifted impulses, k, and it can repeat itself infinitely, right? And it's periodic with, what is the period of this signal? Periodic with T0 equals to what? Just say it. TS, right? I mean, yeah, somebody, I think, wrote it. Thank you, guys. Yes, thanks, Evran. TS, exactly. Periodic with TS. Now, I asked you Fourier transform, but you guys saw that it's periodic. So the idea would be to find or calculate the Fourier transform of a periodic signal. You would find its Fourier series coefficients AK, right? And then take shifted impulses to those k omega 0, right? Multiples of the fundamental frequency. That's it. So we have to first find, because it's periodic, guys. Sorry, I don't want this type of page. Let me add this guy. So let's see. Okay, I'll continue with this one. So guys, because x of t is periodic, signal is a periodic signal, we first calculate AK, i.e. the Fourier series coefficients, then it's easy to find the Fourier transform, okay? First calculate AK in order to find Fourier transform of x of t, okay? That's the idea. So now AK is, just remember it was 1 over T0 or now 1 over TS. Now let's do in one interval minus TS over 2 to TS over 2. So it's really like I'm finding or doing an integral here. Let's maybe show it here, guys. The signal was like this, right? Remember, this was our x of t. Now we are doing an integral in this range, right? These were TS minus TS. Now we're doing minus TS over 2 to TS over 2 integral, right? There is only a single delta in that range, actually. Single impulse function. This was my t. Now let's just finish our integral, okay? x of t, it was actually, this is the definition still, minus jk omega 0 t dt, just, or omega 0, okay, I will insert omega 0 later, 1 over ts minus ts over 2 to ts over 2, delta of t, right, in that range. It's just one of these. This is the centerpiece, delta of t. I just sampled it there. I mean, I'm just integrating it in that range. That's why. And then I know this guy really just samples from the multiplying function, t1 dt, and this is really 1. Okay? And 1 over ts, of course, is that. I mean, integral is 1. That's what I wanted to say. In that range, right? 1 over ts. I mean, the integral limits are still minus ts over 2 to ts over 2. So we used, I mean, here always this is like used sampling property of the delta function. Okay? It's clear, right? This integral is clear. So now I have AK. We found the Fourier series coefficients for the impulse train signal to be really this simple constant 1 over ts. Now from here, my Fourier transform is xj omega is, what was it, guys? For all k, 2 pi, remember ak delta omega minus k omega 0, right? This was the Fourier transform. Insert ak here, and that's it. This was k minus infinity to infinity, so I will have again k 2 pi over ts delta. It's really easy. Now you can see omega 0 was 2 pi over ts, by the way. Now let's insert it for this specific function, right? Signal. Okay, so let's say omega is 0 is 2 pi. So you see, guys, the Fourier transform is another impulse train in the frequency domain. That's the idea. So let's plot this guy. This guy will be really, so let's write, here it's important, another impulse train in this time in frequency domain. Okay? Let's write this. This is nice, and it's actually amplitude changed. Before it was 1. You see, look at the form of the impulse train in time. I plotted here on the left in the middle of the page, right? That was an impulse train. That's the input function. Now this is impulse train in the frequency domain. And it continues in this way. It's periodic. So this is now 2 pi over ts, 4 pi over ts, 6 pi over ts, dot, 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 minus 2 pi over ts, minus 4 pi over ts. Okay? So I want to again ask you this inverse relation between time and frequency at this point. Look at the time domain to impulse train. The impulses were separated by ts, right? Now, here in frequency domain, impulses are separated by 1 over ts. Again, we see, guys, spacing in frequency is 2 pi over ts. Again, as for instance, period in time domain, this ts increases, right? The delta will be, the impulses will be widely separated there, but it will be here now more densely separated, closely separated. That's the idea. So we should say note again. So from this, okay, this is 2 pi over ts interval in frequency domain. Note the inverse relation again. Relation in intervals of the delta, both in time or, of course, both in time. I should not say both for in versus, because that's a versus. Delta in time versus frequency domain. Okay? This is what we are trying to say. We're trying to say TS goes up wider in time, but narrower in frequency. This is what I'm trying to say again, narrower in frequency. And vice versa, of course, right? And vice versa, the other way around. Okay, so I think these number of these pairs of Fourier transform is fine. We've covered a lot of examples or pairs now. We can give a break. Then we continue with, let's give a 10-minute break with properties of Fourier transform, like linearity, time shifting, time scaling. Then we will look at convolution property, one of the most celebrated results of signal processing. Remember, convolution in time domain is multiplication in frequency domain. This is also basis of FFT and frequency filtering. Okay, all those libraries, numerical libraries, probably NumPy has FFT, right? I mean, they all use these fast implementations in frequency domain, guys. Take the signals to Fourier domain, multiply, come back for convolution. That's the idea. You guys have been doing this already, right? In the homeworks. Great. Okay, let's give a break. Let me tease. So guys, now we covered Fourier transform pairs, and we said no to table 11.2 in the SP first textbook lists some of the Fourier transform pairs. Now we continue with properties of continuous time Fourier transform. And the first most obvious property is the linearity. Okay? So please show this. I mean, I'm given two signals, x of t whose Fourier transform is x of j omega, y of t in time domain is Fourier transform is y of j omega. In time domain, take a weighted combination of them, right? Superposition, it applies the same way in the Fourier domain. Now, second one, welcome Fırat. Fırat is here. Fırat, do we need 15 or 20 minutes for the quiz?
We need 15 minutes.
Okay, so we will leave around 11:15. Thanks. Okay. Now, time shifting property. So this means given a signal and its Fourier transform again. So given a signal and its Fourier transform. By the way, I mean, these are both-sided, right? One-to-one relation, time and frequency domain. What is the Fourier transform? X of t whose Fourier transform is x of j omega. What is the Fourier transform relation now to the shifted? How does the Fourier transform of x of t change when I shift the signal? That's the question, okay? So it's gonna be, let me write this, multiplying my Fourier transform by this complex exponential at that shifting frequency, okay? That's the result, and we will show it. Let's just prove. Start with the definition of Fourier transform and insert the shifted signal this time and do a change of variables. I think you guys can guess where I'm going. So let's just say I named t minus t0 as tau. Now d tau is dt, right? So my integral limits don't change. X of tau e to the minus j. Here, from here, t is tau plus t0. Tau e to the minus j omega t0 d tau, right? And this is something that's not dependent on tau, so it can go out, right? That's why you see we have what we already showed. Okay? That's it. So the third, I mean, this is clear, right? Now you guys can show the frequency shifting property, very similar. So shifting this time again, given x of t, x of j omega pair, I'm saying, asking you, if I shifted my Fourier transform in frequency domain, what happens to the time signal? I think you will guess it's gonna be this time weighted by the complex exponential at that shifting frequency in the time domain. This time start the proof, okay, in the Fourier domain, meaning start the proof with the inverse Fourier transform, x of j omega minus omega 0 e to the j omega t d omega, remember, and do a change of variables for this guy. Let's say sigma equals omega minus omega 0. Do the change, guys. I think you can do it. I mean, d sigma is obviously d omega. So I will have 2 pi minus infinity to infinity. From here, I need omega equals sigma plus omega 0, j sigma d omega, right? I mean, d sigma, of course, this time. From here, you guys can see this is really equal to, because this is e to the j sigma t times e to the j omega 0 t. This guy will be independent of what we're integrating here, right? So, I mean, just for your notes, maybe we can redo this. This is, you see, equal to 1 over 2 pi. This guy goes out of the integral. Now our integral is, what was it left with? Xj sigma right? And this is equal to, with its 1 over 2 pi, of course, this is equal to x of t. So, okay, this is it. Another property, guys, this is my Fourier transform we brought from before. A fourth property is the time scaling. Okay, time scaling, meaning time scale my signal. Now, again, x of t has a Fourier transform. Time scale my signal. It could be compress or expand, right? Remember, we were doing this before. It's gonna end up with a scaled Fourier transform and also multiplied by the amount of scaling. But here you see the inverse relation, guys. Note, we will derive this. If I compress in time, it's going to expand in frequency. Or if I expand in frequency, it's going to compress in vice versa in time. And okay. So proof, this is also, this is, you see, all calculus actually. Currently what we're doing is just calculus, change of variables. So let's do the math with the Fourier transform. Do a change of variables. D tau is a dt, right? That's why I have that 1 over absolute value a. So I will need this 1 over a minus infinity to infinity x of tau t e to the minus j. You see t is tau over a d tau. So this is really, you see, what we've just shown, right? This is really equal to 1 over a. This is because x of j omega over a. Okay? Frequency is scaled. Again, here you can recall the relation between this inverse relation, dual relation between time and frequency. Guys, xat versus that. So for instance, x of 2t, let's say, I will have 1 over 2 x of j omega over 2. So this 2t compresses in time, right? It's gonna narrow over in time, or compressed in time. this is wider, let's say wider spectrum. Wider spectrum, frequency spectrum, I mean. In frequency, vice versa. I mean, if I had, for instance, x of t over 3 or something like this, which is wider in time, right? Now I would have 3x of j, 3 omega, right? This would be now narrower in frequency, right? It's compressed itself to 1/3. This is narrower. I mean, there is some scale, but important thing is here the axis, narrower in frequency. Okay? This is wider spectrum, we said. And now this is narrower in frequency. Okay. This is good. Maybe I can do 1 or 2 more examples and we can leave convolution property to next time. Okay? This is straightforward, but don't worry, you're seeing it for the first time. It may be not still that easy to follow, but still, let me see, yes. Try to please at least follow what we're doing. We're now listing or driving the properties of the Fourier transform, okay? So if I, okay, 5 we said time flip, but this is actually really using this previous property, which means what happens now to x of minus t? Just x of t goes to x of j omega. X of minus t would be really x of, again, I mean, it's a flip in frequency, right? I just use this property here, guys. Used xat, remember it was 1/a x of j omega over a. Here a was -1, right? With a equals -1. Right? Guys, we used, okay. I mean, we used previous property. Okay. We can also show, or let's see, calculate, okay, in frequency domain, for instance, the frequency spectrum or Fourier transform value at 0 frequency. So this is Fourier transform at 0 frequency. We just apply the definition of the Fourier transform here. Just do the math. X of t e to the minus j omega t dt. We set it to omega equals 0. That is the area underneath, right? The signal. Minus infinity to infinity x of t dt. Because omega equals 0, this becomes 1. Right? So this is really area under the signal. So the area under the signal gives me its value, the Fourier transform value at 0 frequency. This is in frequency. In time, you can do vice versa. You see everything has a duality, little x0. This time I can use 1/2 pi minus infinity to infinity. Now I can look at the Fourier transform of the signal. And okay, this is going to be 1. The area underneath the Fourier transform divided by 2 pi gives me the signal value at time equals 0. I mean, this is really just applying the definition. So this is really, we should say 1/2 pi minus infinity to infinity x of j omega d omega. So this is really area under Fourier transform x of j omega, of course, over 2 pi, is giving me the signal value at t equals 0. I mean, this is really some signal mathematical manipulation to show these. I think we should be fine. Like I said, we can look at other properties, a few more properties next time. Then I think we could study maybe again filtering a little bit, sampling, and we should look at some Fourier transform calculations next time also. Okay, we will do some more mathematical calculations and go to some applications like sampling. Then we go to discrete time Fourier transform in the other week probably. So I think that should be it for today. Any problems, any questions? In today's quiz, of course, you are not responsible from these. You will have a frequency response. You will have 2 frequency response questions. Fırat, you can upload actually if you want. I can stop the share. We are fine, right? Any questions, please ask. I could stop the recording at this point and we could go to the quiz. Guys, we continue with continuous time Fourier transform next time. Probably go to discrete time Fourier transform the next week.